Hi, I'm Brendan, and in this video, we're going to be talking about data hazards. So before we get into it, let's start just from the bottom. So what even is a data hazard? So data hazards occur in the pipeline implementation of a data path for instances such as this. So when we look at this code, we see that the first instruction, we're adding registers 1 and 2 and then storing it into register 3. And then in the very next instruction, we're using register 3 to add it to register 4 and then put it in register 5. So what's the problem with this? The problem is that we are storing a value in register 3 and then immediately using it for the next instruction. And that's a problem because of the way that this particular pipeline is implemented. So remember that when we complete an add instruction, when we're writing back to this register 3, that's not going to happen until the write back stage. But when instructions fetch register values, so for example, when this add instruction is going to get the value of register 3 and register 4, it's going to do that in the ID stage. So that means that we're going to have an add instruction in the ID stage, and then this instruction is going to be in the EX stage. But that means that the value of register 3 hasn't been written yet in time for the next add instruction to then load the value of register 3. So that's why these two registers are a problem. And that's called a raw dependency or a read after write data hazard, because here we're trying to read a register after we just wrote to it, and that's what causes these problems here. And so there are a few techniques that you can use to handle these data hazards. So let's walk through the most simple example, and that is called avoidance. And so what avoidance says is that it's really on the programmer to understand the implementation of the pipeline of the processor to make sure that they don't even write in any data hazards into this code. And so what that would mean is that if I was a programmer trying to write this program, I would have to insert some no-ops to remove this data hazard. And so what I would have to do is I would have to insert 2 no-ops right here in between the 2 add instructions in order to avoid the data hazard. And so that kind of begs the question, why 2 no-ops specifically? So again, going back to our pipeline, we know that the second add instruction is going to load the register values here, but we're not going to be writing back until the 5th stage. So that means that we need to stall 2 cycles, so insert 2 no-ops into our code, which would be here and here. And so then we would have the final add instruction here, or the first add instruction here, and then it'll write back to the register file so that the second add instruction can load those values. And so this can be a little bit confusing at first, and I think the most confusing part is why we don't insert 3 no-ops as opposed to 2. So we're kind of assuming here that these register files have what's called internal forwarding. Basically, all that means is that within the same cycle, you're able to write back to the register file and read those same writes in the same cycle. So that's why we don't have to wait for this write back to completely finish, and we can do the instruction decode in the same cycle as the write back itself. Now, this is an assumption that does not hold true for project 3 if you're working on that, just because internal forwarding is pretty challenging to implement with code, so we don't worry about it in project 3. And then in that case, you would insert 3 no-ops because there's no internal forwarding. But because there is, we only have to insert 2 in this case. And so when I say insert, again, that is the programmer inserting these no-ops into the code before the code is even pushed onto the pipeline. And that kind of is a good transition into the second technique here, which is detect install. And so detect install is just like avoidance. You would insert the same number of no-ops in each case, depending on how far apart the instructions are. But in the detect install case, it's not on the programmer to insert these no-ops. Instead, that functionality is added to the pipeline, into the hardware. And so then the hardware components will be able to detect when there are these data hazards, and will insert as many no-ops as needed. And so again, these two are very similar, but avoidance is on the programmer on the software side, and detect install would be already implemented into the pipeline on the hardware side. Now, detect and forward is typically the best solution for us to handle these data hazards because it takes advantage of the way that the pipeline is structured to get values sent back earlier, so we don't have to wait as many cycles as we did before with avoidance and with detect install. So let's take a look at the pipeline to see how this would work. So remember, we have these two add instructions. And so let's see, when the first add instruction, which let's just label instruction A, and then we have the second instruction, which we'll call B. So we're really concerned with the value that will be placed in register 3, right? That's the value that we need to access in this second instruction and the value that is causing this data hazard in the first place. And so if we take a look at our pipeline, we'll see that when instruction B is in the decode stage, we'll have instruction A here. And so after instruction A completes the execution phase and actually generates the result that will eventually be stored in register 3, that value will be ready. We don't really need to wait for it to be written back to the register. So on the following cycle, after this cycle where instruction B decodes and instruction A completes the execution, we'd see that instruction A would move on here, one stage in the pipeline, and then we would have instruction B in cycle 3. And so now what detectin 4 takes advantage of is the fact that we have the value of register 3 already calculated. And now that is somewhere stored in here in these internal register files, sort of like these, you can think of them almost as like temporary buffers, temporary variables. And since we have that value ready, what we can do is just send it back to the EX phase. And so we would take the value that register A just calculated and then use that for the calculation as opposed to loading what is now really a garbage value that instruction B originally loaded from register 3 in the ID phase. So we basically use the hardware of the pipeline to override what we already loaded in the ID phase. And so this allows us to really eliminate most of the no-ops we would have to insert with detect install. Now the only exception to this is when we have, instead of an add followed by an add, if we have an LW as our write, and then have a read after that. Because for all the other instructions, their destination register is calculated in the X stage, but for LW, we're loading a value from memory, which doesn't happen until one stage later. So we have to stall one cycle in that case. So let's take a look at some timing diagrams so we can see some more examples of these data hazards. So let's draw out the timing diagram first for a detect install type resolution for data hazards. So when we're looking at detect install, remember that we need to look for any of these raw data hazards, any of these raw dependencies. So first off, we have this first add instruction, and we're just going to assume here that this is the first instruction that's being executed by the pipeline. And so sort of trivially, this can't really depend on anything else because it's the first instruction. So what we're going to write here is the different stages that each instruction will be at during each cycle of the pipeline. So since this doesn't have any hazards or anything, we're really good to go to execute all 5 cycles of this instruction immediately. So remember, first we have IF, which is instruction fetch. Then we have ID, which is instruction decode. EX, which is execute. Then we have MEM, which is mem. And then WB, which is write back. So this first instruction, we're able to just execute all the stages without any worry for hazards. And now for NOR, to check the hazard, we look and see that the registers that are using these values 4 and 5, so those are values that would need to be fetched in the instruction decode phase, we'd look to see if those had just been written to. And in this case, they haven't, because register 3 is not one of the registers that NOR uses. So again, we're good to go to just write out the 5 stages here. But now for this add, we see that add uses register 3, which was just written to by this add over here. So we'll see that normally what we would do is we would have in the next cycle, cycle 3, we're going to fetch the instruction, and then typically what we would do here is a decode. But I put a little asterisk here because we're not really ready to send on this add instruction yet, because we still haven't fetched the correct value that needs to be in register 3, because at this point, the first instruction is still in the mem phase, and we need to wait for the first instruction to write back the register before we can use that value. So that means that we'd have to stall one cycle here. So I just put an ID asterisk to represent that we're basically holding back this add instruction in the ID phase. And so then in cycle 5, this instruction will still be in the ID phase. And now we're good to go because in the same cycle, we're writing back to register 3. And again, assuming internal forwarding, we're able to use that value in the same cycle. Now after that, the instruction will complete as normal. Okay, great. So we got those first 3 figured out. Now let's look at this SW here. So we have in cycle 4 a spot for it to go into the instruction fetch. But since the add instruction before it is getting held back in the decode phase, we can't push the SW on. So we have to also stall the SW because we can't just like have the SW instruction running on top of the add instruction. So we have to hold the SW back one as well, in addition to all of these really because of the delay that is caused by the add instruction here. So now for SW, we would be storing what's in register 6, and we would store that into memory at a location stored in register 0 plus the offset. And so the offset isn't a register, so we don't have to worry about this, but we do have to look at these registers. We see that there aren't any hazards caused by register 0, but there is one caused by register 6 from here to here. And so again, typically what's going to happen is we would be having to stall 2 no-ops here, but we'll see that because we already stalled 1 no-op here with this add instruction, it works out that we don't have to throw in an additional 2 since we really already incurred a loss over here. And so really, again, what we have to do is line up the write back with our instruction decode. And so when we're stalling the instruction fetch here, we would end up finally being able to push on the SW to actually fetch the instruction in cycle 5. So we're staying in instruction fetch, but now after this cycle, we'll be able to move on. And so then in this cycle, we would do the instruction decode. And so now we see that this is lining up with the write back that we need. And so remember, we'd have to have at least like 2 cycles in between. And so this add takes up one of the cycles, and then the no-op that this add also had to insert for its own data hazard was the second cycle. So we don't really have to do anything additional for this SW instruction here. And so now this will be able to complete. So now for LW, the register that we would have to be concerned about is only register A, because we're loading the value in memory that's stored at the value of register A plus the offset, and we're storing that into register B. So register B can cause a hazard because that's a register that we're writing to. So it can cause a hazard later on for future instructions, but not for its own instruction, not at this PC. And so again, we're not storing into register 0, so LW will be safe to execute. So what we can say here is that the LW would fetch alongside the when SW finally gets pushed onto the decode, and then it'll execute as normal. And so now finally, we have this add, and so we have this register 7 that's trying to read a value that this LW just wrote to. So now LW is unique because register B is sort of the destination register, that's what's written to, and now the add is trying to use that, we have another raw dependency. And so now we have to wait for add has to wait for LW to write back to register 7. And so here in this case, we'd have the add would go to fetch, and then it would have a hazard, and it would see that here in the decode phase, and so we'd have to stall. And then in this cycle here, we see that this value still hasn't been written back. The LW is still in the mem phase, so we have to stall again. And then finally, we can decode the instruction when the LW is in the write back phase. And then this instruction can complete as normal. So this is the timing diagram. If we were to try to execute this program with a detect and stall implementation, let's see how we would revise this if we were using detect and forward. So now if we're looking at a detect and forward type solution to solving data hazards, we see that just looking at the beginning of this timing diagram here, we're able to resolve a lot of these without having to incur any penalty, no incident, no ops, and no stalls whatsoever. So just looking at one example in particular with this add here, we still have the same raw dependency and the potential for a hazard here. And so let's look at what we think would happen here. So now, when this instruction is in the EX phase and it's trying to use the value that's stored in register 3, with our detect and forward type solution to solving data hazards, the pipeline would detect this hazard, and instead of using the value in register 3 that it loaded from the instruction decode phase, instead, the pipeline is going to forward that value back. And so it's going to forward it from the add instruction back down to this add instruction down here. So it's not going to have to wait in the instruction decode phase to line up with the write back. We're just going to be able to pull that value while we're executing, and we don't have to wait for any stalls. And so remember, that applies to all cases except when we have a dependent instruction that immediately follows an LW. And so that occurs in this last case right here. So remember, we have this register 7 that depends on LWs storing into register 7. And LW, again, is unique because the value that will be stored in this case in register 7 isn't ready until after the mem phase, as opposed to after the EX phase with all of the other instructions that store somewhere into a register. And so now in this case, when we have our add instruction, what we would have is the instruction fetch would occur while the LW is decoding. And then when we go here into the instruction decode phase for add, we'll see that we have a hazard here with the LW, and so now we're going to have to stall just one cycle. And so we'll stall here, and so then we'll be able to move on the instruction, and we'll say that we have the instruction decode. And so now we'll see that this is when LW is in memory, and so after this cycle, the value will be ready for the add to use, and so then we can have the add move on into the EX phase here. And so now the add instruction will be able to use the value that was loaded from memory. And so then we will have the add instruction be able to complete as normal. And so now this program only incurred one no-op, so only one stall. So you can see that the detect and forward was able to solve this problem of data hazards a lot more efficiently than avoidance or detect and stall was able to. I hope you learned something new today and have a better understanding of how to solve data hazards when it comes to pipeline data paths.